So another type of graph that you need to know are the trig graphs. Now, we all know the trig buttons on the calculator, and we all know how to plot graphs. What we could do, or what I could have done, what I could have done if we had loads of time, is I'd get you to choose values of x, perhaps 15 degrees, 30 degrees, 45 degrees, so on and so forth. You hit sine that number, sine 30, sine 45, and plot all those points. And you get to draw them. We really don't have time for that business. So I'm going to just show you what they look like. Okay? Now, two of the graphs, the sine and the cos, both look like this. Okay? When I say they both look like this, they start at different points. And that's what we'll talk about. These are features that I want you to be aware of. So this middle line here, we call the principal axis or the central line. Okay? So as you can see, the graphs go above and below it at equal distance. Now, the amount that they go above and below that central line is called the amplitude. Okay, so the amplitude of the graph is how much above or below it goes from that central line. We have maximum points, we have minimum points, and then this part here is known as the period. That's how long does it take to go from start to finish of one complete cycle. Can you see that that's a cycle? So up, and then it keeps repeating. So that would be known as its period. Okay? So that's just some terminology that you need to be aware of. It's all said here in this blue box here. Okay? So the sine graph, as I said, I could have got you to plot points, I'm going to. The sine graph starts here at 0, 0. Because this, if we press sine 0 in our calcs, it would tell us the value of 0. If we press sine 90, it would tell us the value was 1. Sine 180 would also be 0, and sine 270 would be -1. Sine 360 would be back to 0. So our cycle, our period for this graph here would be 360 degrees. Okay, so for the sine graph, the period is 360 degrees. Okay, that's how long it takes to do one cycle. For this original graph, so just basic sine x graph, the central line is the x-axis. What do we think the amplitude is? So pardon? 1. Yeah, do we all see that? I'm not sure what you said. You said 90? Just by accident. So our amplitude is 1. No. So I appreciate that it goes up to 1 and down to -1, but the amplitude is just the distance. Okay? So that distance is 1, that distance is 1. Does that make sense? Yes? Because we're talking from the central line, it goes down to -1. Now, obviously these are basic graphs. If you're ever asked or need to look at the amplitude and it's not quite so obvious, the amplitude will always be the distance from the central line or half of the total distance. So we can say that we've gone here from 1 down to -1. So that's a whole measurement of 2. Therefore, half of that is 1. Okay? Hopefully you're thinking, oh my god, this sounds really easy. Why is she going on about it? Okay? But when they start moving, then it starts getting a bit more complicated. Cos curve. Okay? You see it looks exactly the same, but the whole thing is just shifted across. Okay? So the cos curve starts up here at 1. Okay? If we did cos of 90, it would be 0. Cos of 180 would be -1. Cos of 270 would be 0. Cos of 360 would be 1 again. Okay? So a complete cycle for the cos curve is still 360 degrees. So our period is still 360 degrees.
It's not 270.
No, because we have to see where it starts and finishes a full cycle. Yeah. So you see here, because it starts up here at 1, where does it finish at 1? Yeah, so it has to be a full cycle. Does that make sense? Amplitude. What goes up to what and down to what? 1. A 1, so our amplitude again is 1. Okay? So those two graphs are super similar. Now we're going to look at Mr. Tan. Alright, okay, so tan graph, as I said, not quite the same. Okay, aka totally different. This graph here looks like lots. What kind of graph did we draw yesterday that looks a bit like this?
I can't remember.
It's called a cubic.
A cubic.
Cubic, yes?
Right.
So this looks a bit like lots of cubic graphs, yes?
What was the other name? I was more.
Oh, there's still a cubic, but this is just our basic x cube. Okay, this is not x cube, this is tan, but it just looks similar to it. I was just trying to help remind you. Okay, so these look a lot like the lots of x cube graphs. There's gaps here. What did we say it was called when we have gaps in graphs?
Asymptotes.
Nice. Oh look, I'm reading it. Okay, we have asymptotes at 90 degrees and at 270 and at negative 90 and so on and so forth. Okay, so because these graphs keep repeating, these features also keep repeating. So these are asymptotes.
How do you spell A?
There you go. Asymptotes. Asymptotes.
Totes?
Totes. It's at the bottom of the page.
Wait, is that T-O-K-S?
Let's go. It's at the bottom of the page.
T-O-T-E-S.
Okay. So there, and the reason that we know that they're there is because if we typed into our calculator tan 90, your calculator would say mathematical error. It would say that it was impossible. Okay, so if you type tan 90, yeah, it would say error. So here's our graph. Period. So remember, we're saying how long does it take? I mean, at some point, someone was going to laugh. And we also talk about cycles. Like, why?
It's like a phrase.
Oh,
Period.
Okay. So, oh my gosh. So, how long is the period for the tan graph? How long does it take to do a full cycle? Is it another 360?
No. Is it 90?
180.
So Amelia's suggesting 180.
Yeah.
Jodie's suggesting 90. Alright, so we need to decide how long does it take to do its thing. So we can, I mean, it doesn't matter where we look at it. So I can see that this does a kink thing here and another kink thing here. So its cycle for this one is the kink, yes? So if it starts doing it around here and ends it around here, how much is that?
Ends it around where?
Here. So it's
180.
so that's a distance of 180, yes?
What?
How do you
I thought it's under 180.
Okay. But I hear you. However, the asymptotes do repeat at 180, so that indicates that the
But there's no asymptote.
no, they don't. However, these.
The line.
Did you say there's no asymptote?
After 180. Because there's no gap.
No, Angel. Every 180 degrees, they repeat the asymptotes. Oh, not at 180,
Yeah,
every 180
Okay.
degrees. So, and remember, well, maybe I say remember, these graphs keep going on and on and on down here, okay? So they are going to get super close to that point, but they just won't ever touch it, okay? So whilst it looks like it's nowhere near it, way down here, it would be really, really close to it.
So if you go on for infinity, won't they get in touch?
No,
No.
it's the nature of graph.
I don't know if it's part of that.
Yeah. Well, it's become really, 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 really.
But then it didn't never
No, but ladies, because the asymptote repeat of every 180, the period of this graph is 180 degrees.
So you measure, you measure by the asymptotes and not by the actual line. Since they get circles.
Sure. Yes. Let's do that.
So figure out.
This is hilarious. This is the first year in my many years of teaching that people have like fought me over the period of
So what do you do first when you're looking at the period? You just do 0, you just start at 0, and then you say,
No, you don't have to look at 0. You just need to look at how long does it take to complete a cycle? How often does it repeat?
or how far apart are the asymptotes?
Or for this one, how far apart the asymptotes?
So it's not always going to be 180. So it's like the first one going on.
Hang on a minute. What do you mean it's not always going to be 180?
It's always 180 for every period of 10.
Yeah, it is.
Why? How is that confusing? Like,
Because it's not going to be 180 for all of them.
yeah, that's what I'm trying to say. So it's not going to be like if this isn't a rule, like it's always 180 for every period.
The tan x graph, the period is 180 degrees.
Oh, so it is.
Yeah.
The only one's the left.
Okay, so it's going to be fine.
Yeah. Can you come here and take your thumb Okay, I'm going to show you.
On and on. So it's
Yes.
infinity.
Yes. I'll get to that bit. Alright, so my next question was what's the amplitude? So, did everyone hear what Emily just said?
Yes.
So because it just keeps going up, there is no, or we would just say there's no amplitude.
What?
We don't identify it. Because it goes on forever.
write infinity?
Sure, you can write infinity if you like.
Well, where would the amplitude be?
So remember, the amplitude is from half of the top to the bottom, and because there is no top or bottom, you can't measure that.
I thought it was from the top to the middle line.
I said half of the top to the bottom, which is the same.
And there is no bottom, it's just like forever.
Correct.
Which I don't understand how that can be possible. Like it doesn't make sense how someone can just go on forever. Like that just doesn't make any sense.
Okay, so I see part of my issue why I'm a little bit behind with Latham's Not only are we missing lessons, we also have like 16 hours of that stuff. Oh my gosh. And it wasn't a attack on you, Emma. I like the fact that you're questioning things, but I'm just a bit sad when you're so tired.
Oh, you did
You won't just kind of accept something. Alright, okay, so as I said here, there are those asymptotes at 90 to 70. Alright, so
Oh God.
this stuff here, it looks super complicated, and I'm really sorry, Emily, that yours is no longer in colour, because I think the colours kind of help. So here we've got our sine graph, okay, so this is for sine. If you typed into your calculator, oh I'm so sorry, sine 65, okay? So if you typed into your calculator sine 65, you get a value up here. I can't even remember what it is. I think it's 0.87.
0.9063075.
I'm so sorry, what is it?
0.9063075.
Okay, send me different rating. We'll stop there. So 0.906. So it's up there, okay? Now, hopefully you can see that the graph, the sine graph, also has that value here.
I put
You type into your calculator sine 65. Okay? So if you were to type in your calculator sine 65, you would get 0.906. Can you all see that the value here would also give you the same answer because it's at the same height. Okay, so the blue graph is at the same height over here as well. It's also at the same height way down here and further and further and further because it keeps going on and on forever. That means that we have multiple values or multiple values that we can substitute in to get that same answer. Now, in some cases, you'll be asked what would those values be, okay? So if they said sine 65, what other value of x could you get for that same number? You would have to be able to tell. Now, the best way to do it is to use symmetry. Can you see that this bump here is symmetrical?
Yes.
And that our line of symmetry is down here through the 90. So if this portion here represents 65 degrees, hopefully you agree that this portion here would also represent 65 degrees. Oh, Jodie's thinking.
I'll get it eventually.
So if this represents 65 and this is a line of symmetry, this would also represent 65 degrees.
Yeah.
So therefore, because this point here is at 180, then this value here must be 180 subtract 65. Yes?
Wait.
So this number here is 180. This represents 65, so this actual number would be 180 subtract 65.
What actual number? Like that actual
This place, this position along the x-axis.
But did they give you the 65?
Yes. So they would say sine 65, what's another value, what's another angle that would give you the same answer? Okay? So there's our axis of symmetry. It's 180, subtract that. Yes.
If the line of symmetry, doesn't it go from 90 to 180? So isn't it just 90 between? No.
Well, it's 90 between here and here, yeah. I'm sorry, I'm not sure what the question
Yeah, I
So
thought
line of symmetry go from 90 to
doesn't touch the
180.
Oh, yeah.
Yeah?
Yeah.
Thanks, Jude. Right, you happy with that? I don't want to talk about these, but just because for this upcoming thing, and they don't come up very often, this just looks way complicated, and I just think for the first thing in the morning, we're all going to cry. Well, it totally is. However, you just have to work with different numbers. Shall I go through it? All right. So for this bump, sorry, Des, you can't really see. For this bump here, our line of symmetry is down through here. Yes. So that's at 270. So if we were saying, right, okay, our angle for this time is 250. Okay? So if it's 250 degrees, then from this point, that's 70. Yes? So our 250 degrees from 180 makes that fit 70, which makes this fit 70, which would make this number here 360 minus 70. So in other words, 290. Okay? So here, for this one here, we can say that sine 65 is equal to sine 115, and sine 250 would be equal to sine 290. Okay? It's just using symmetry on your calculator. Symmetry, not on your calculator. Good lord. Cosine's a little bit easier because there's just one line of symmetry. It's smack bang through the middle. Okay? So for our line of symmetry for cos, if you have an angle here, 45, then the same value here would be 360, subtract that number, because our line of symmetry is here, so this represents 45, that represents 45. So cos 45 would equal cos 350. Okay? That was a lot easier. Tan. Okay? Tan is also a nice easy one because essentially all you have to do is add 180 to all of your answers, because there is, for each tan portion, so for each tan cycle or period, there's only one value that gives you that answer. Does that make sense? So there's no symmetry in this, okay? So if we've got tan 65, then the next one is going to be at 180 plus 65. Okay, so for the tan graph, you're just always adding 180 to your values. Okay, so tan 65 is equal to tan 245. Okay? Whew, that was actually not so bad. Okay, I'm going to pause it here. Girls, I just want to, don't fight please. So I just want to add a couple of tips how to draw these graphs. Okay? Okay, there's my axis. You're going to have that kind of axis for all of them. The main points you're looking for are 90, 180, 270, and 360. Hopefully you recognize that they're all multiples of 90. Yes? So 90, 180, 270, 360. For the sine graph, we know it starts at 0. We know the maximum point is 1 and the minimum point is -1. So it's at 0. At 90 it goes to 1, then down to 180, down here, and back up here. So if you've got those 4 points and you know it goes from 1 to -1, you can just do that. You see that? So 90, 180, 270, 360, up, down, down, up. Okay? Because super similar. 90, 180, 270, 360. We know it goes up to 1 and down to -1, but this time it starts up here at 1. So it goes to 90, down here, up here, up here. There's your cos curve. Okay? So you may want a little bit of practice doing that. When you have a question like these, you may want to do that and try and visualize what's going on. Now, if you don't remember which one starts at 0 and which one starts at 1, we know it keeps going, so this kind of makes a C through the y-axis. This one makes kind of S through the y-axis. Okay? You can remember it however you want to remember it, but that's how I often think is a good way. So the sine goes through 0, 0, cos goes through the point at 1. So that's your sine and cos. For your tan, which is less common, you're still going to do 90, 180, 270, and 360. You're going to draw in your asymptotes at 90 and 270. You don't need to write any numbers here because there is no amplitude. You then do a swoosh up, and a kink, and a swoosh up. Okay? All of those swooshing words are not helpful, but hopefully you saw what I was doing. Okay? So it's like a kink up, a full kink, and a kink from the bottom up to the middle. Okay? So that's your sine, your cos, and your tan graphs. Okay? We know that they keep repeating, so there you go. Okay?